Hello everyone, so welcome back. So in this video we are going to break down the definition for convergence of a sequence, the definition that we are going to learn in real analysis class. But before that, let's recall what we learned in our calculus class. So in calculus class we learned that a sequence is convergent if it has a limit. If it has a limit exist as a real number. So let's look at an example. If we look at this sequence, we can write it as S sub n, it's 1 over n, right? Now the n belongs to natural number system. Okay, so if we take the limit of this sequence when n goes to infinity, 1 over n, the limit is 0. 0 is a real number, so the sequence is convergent, right? Now what do I mean by a sequence to be convergent? Well, if we keep on writing these terms of this sequence, what happens is that we get closer and closer to 0. We really approach towards a real number. So that is what convergent means in simple words. Okay, now if we look at the definition that we use in our real analysis class, it looks mathematically complicated, but really it should be something that makes sense, right? That fits to the understanding or the idea of convergence. So let's try to build it up by ourselves. Now let's use the same example, and also we can use this example because we already know that this is a convergent sequence, right? It's convergent to 0. Alright, so here's what I'm gonna do. What I'm gonna do is I'm gonna take each term of this sequence and calculate the distance from each term to its limit. So let's take the first term, 1 minus 0. So 1 minus 0 is 1. Now why do I need absolute values? Because distance is positive, right? So I make sure I have absolute value. Alright, now this is the first term. So from first term to the limit is 0. So let's call it S, okay? Not S sub n, limit is S. So limit is 0, so the distance from first term to the limit is 1. Distance from second term, which is half, to 0 is half, because 0 is the limit. 1/3 minus 0, the third term, 1/3. So let's write this as 0.5. This is around 0.3 roughly. 1/4 minus 0, it's 0.25. Okay, now what I'm doing here is, like, let's say you are driving from Chicago to New York. So every now and then you check in your Google map to see, well, how closer I am to my destination, right? So similar thing happens. So for every term of the sequence, I'm looking at how closer I am to the destination or to the limit. All right, now we already know the sequence approach to 0, convergent to 0. Now what is a characteristic that convergent sequence have? Let's see, convergent sequence has. So let's see. Let's stop at the second position. We can confidently say something here. Now, if you can understand what I'm going to say here, if you can understand the characteristic that I'm going to present here, you can easily understand the definition. Okay, so we are going to build up the definition. I can say, after second position of this sequence, so for any position after the second position, that's what I meant by here. Second is 2 is the position. Any position n greater than the second position, I can confidently say the distance between the terms of this sequence and the limit is 0, is definitely less than 0.5. Do you agree? So if you look at the so this is the second position. Let's put a boundary there. So after second position, you can see the distance between the term of the sequence and the limit are guaranteed to be less than 0.5. Now I can do the same for the third position. So after the third position, for every position, the distance between the terms of the sequence and the limit are guaranteed to be less than 0.3. Okay, now, well, that's an interesting relationship, right? Now let's try to write, okay, let's try to give us the distance by ourselves, right? So here I started from the second position. I started from the position. So let's try to go reverse way. I want to know the position of this sequence, where after that position, what is the position number where I get closer, like closer than 0.01? Well, you know, after the 100th position, because the 100th term is 1 over 100, right? So the distance will be 0.01. So after 100th position, I am guaranteed to have the distance between terms of the sequence and the limit guaranteed to be less than 0.01. Do you agree? Yes. Now here the difference is I started from the distance. Let's do one more to make sure. Let's do one more to understand it. Let's give a very, very small number, 0.00001. So tell me the position where after that position you are guaranteed to be even closer than this. What is the position? What do you think? It is 1, 2, 3, 4, 5. So since this is an easy example of a sequence, we can say it, right? After 100,000 position, you are guaranteed to be even closer than this much. Now that is exactly the characteristic that a convergence sequence has. Now think about this. For any distance that you give me, for any closer value, no matter how small of a distance you give me, how small of a gap between the limit and the terms of the sequence that you give me, you can always find a position in this sequence. Always find a position in this sequence where after that position your terms are even closer to the limit than the accuracy that you gave me. Okay, so that's the characteristic that a convergence sequence have. It's getting closer and closer. The idea of getting closer and closer, or idea of approaching to a real number. Now let's look at the definition. Now definition says the same thing. Instead of using numbers, they use the letters. Okay, all right, so let's see. For every epsilon greater than 0, so that's the accuracy that we choose, 0.01, 0.001, 0.3, 0.5. So for any positive number, distance is positive, so that is why they say epsilon to be positive, right? That makes sense. For any positive number that you provide me, or let's think about, let's say it like this, for no matter how small epsilon is, there exists a natural number n. That means there exists a capital N position such that after that position n, for all the positions after that position n, larger than that position n, you are even closer than the epsilon. Your terms of the sequence are even closer to the limit, closer to the number s, even more than epsilon, even more than the accuracy that you give. So this is a characteristic that a convergence sequence has. Okay, so this is the idea, so this is the definition, and it is something that really makes sense if you take time to understand it. And usually in my experience, we do not take time to understand it in our real analysis class, rather we try to memorize it. But if you spend enough time, it's something that can make sense. Now it makes sense very easily because we choose a simple, easy example, right? But in future we are going to take complicated examples and understand it furthermore. But before we close on this video, I forgot something. I want to state a final thing. Now can I make a relationship between epsilon and n? Here's a question for you. Is epsilon and n independent? Okay, if it is not clear, think about it from an example. Is 0.5 and 2 independent from each other? Is there no connection between this number here and this number here? There is a connection, right? This position depends on epsilon, right? So capital N depends on epsilon, right? So that's one thing to remember. Sometimes people write it like this also to show that the natural number in the position depends on epsilon in this definition, and it makes sense why it depends. Okay, all right, so in next video we're going to discuss where we are going to prove actually that the limit is unique. So I will catch you in that video. Until then, bye bye. Thank you.